Okay, so the next speaker is Alessandro Barp from Imperial College London. And this is a talk on geometry of measure, preserving flow on Hamiltonian Monte Carlo.
Thank you. And thank you to the organizer for this summer school. So my talk is going to be in spirit actually very similar to yours, in the sense that I'm going to talk about past heroes which have been forgotten but whose ideas are very important in statistics. And in my case, the heroes are Poincaré, Kosul, Georges Derame. And so no, they're famous in yeah. And we're going to connect essential ideas from statistics to geometric mechanics. And so yeah, the plan of the talk is just to, basically remember that one of the big problems in statistics is that we want to sample from a measure. And typically this is done using some kind of measure-preserving flows. For example, Moulin talked this morning about measure-preserving diffusion, the overdamped one. Another one is the underdamped Langevin diffusion, which is measure-preserving. We also use mechanical flows in HMC, Hamilton and Monte Carlo, where we use Hamilton mechanics to make proposals. There's also some kind of metriplectic system in thermodynamics, which can be used. But essentially, all this process, we can think about continuous measure-preserving systems. So I'm going to talk about that. I'm going to talk about a recent paper in RIPS in which they derived a complete recipe of all measure-preserving diffusions. So basically, if you have a measure on Euclidean space, which is expressed with respect to the Lebesgue measure, and you have a diffusion process which preserves it, then the diffusion process has a specific form, which gives you essentially a general form, basically recipe to build measure-preserving diffusion, which you can then use to sample. And we're going to make some connection with Poisson mechanics because we want to generalize that result to manifold. And inspired from these Poisson mechanics analogies, we're going to develop the geometry of smooth measures. And using this geometry, we're going to build the general recipe for measure-preserving systems, diffusions, dynamics, and mechanics. We're going to make some connection between measure-preserving flows and Hamiltonian mechanics. And then we're going to, if there's time, discuss a bit the construction of Hamilton Monte Carlo and its implementation. And if you have any question during the talk, just, I know it's a bit hard with the mask, but yeah. Okay, so we're given basically a target measure P, which we're going to assume essentially is smooth, in the sense that we can, so in Euclidean space, smooth would just mean that we can write it as a density with respect to the Lebesgue measure. In our general manifold, it means it's a one density. And we're going to assume basically we have some kind of globally supported smooth reference measure mu m, and we have a density. And often, as Moulin said, we only know P up to normalization. This is very important for Bayesian inference. So we're going to assume we only know P infinity up to normalization, or the potential V up to additional constant. And so we have this target measure on a manifold, and we want to generate some samples. And the end idea is that we want to approximate P with some empirical measure associated with some Markov chain. And we want to essentially approximate the expectation of function with this empirical thing. And so obviously the main motivation is, a big motivation is measure on Euclidean space, but actually measure on manifolds appear a lot. In molecular dynamics, they appear when you have molecular constraints, and so you have a distribution holonomic manifold. In statistics, in directional statistics and Princeton computational analysis, you have measure on Grassmannian manifold and Stifel manifolds. In gauge theory, we have measure on gauge groups, which are actually the motivation for HMC. And so we want to have some things which work on any manifold. Okay, and just so basically two standard strategy to build the samplers, some of which we've seen this morning. Basically, one is to just start with a deterministic proposal. So you have some numerical integrator on the sample space, and you want to combine it with some kind of map, which is P-preserving, which preserves your map, and such that together your integrator psi is reversible up to this map S. And when this is true, so when you can find such an integrator on such a S, then you can do some kind of Monte Carlo. So which means that you can sample, you can construct a Markov chain which leaves stationary your measure, by following the following algorithm. First, you start with a given point on your sample space. You make a proposal using your integrator, and then this proposal is accepted with this probability, where J is the Jacobian. So basically, you pull back your measure with respect to integrator, and you take the radon-Nicotin derivative, so it gives you a function. So you accept this point with this probability, minimum of 1, and the Jacobian evaluated at QL, or else you reject it, but you flip. You use that S, which you apply, and then so your next point is basically S of Q, of your initial point. So that's one strategy which builds on deterministic proposals for Markov chain. And another one, which Moulin talked about this morning, is to start with some kind of p-preserving diffusion. And then you can do a lot of things. You can try to just approximate it. If you don't want to do a Monte Carlo step, that's fine. Or you can try to break it into tractable p-preserving components. So for example, HMC starts with the second order underdamped Langevin system, which is this equation on position and momentum. And one part of it is Hamiltonian mechanics, and one part of it is the OU process. Both of these processes essentially preserve a measure on the tangent bundle or cotangent bundle above your sample space. And therefore, you can basically combine them to make a proposal. And HMC is built essentially on combining this with the symplectic integration of Hamiltonian mechanics. So that gives you kind of HMC, when then you add the Monte Carlo step here. So these are the two kind of general way to build Monte Carlo methods. And an important thing is that often samplers are inspired by physics, but for example, this one. But we are not interested in the physical interpretation or necessarily following the physical trajectory exactly. We just want essentially to make a proposal which gives you a Markov chain with invariant measure P and just sample. Okay. Okay, so in 2015, essentially, so this is the NURBS paper in which they proved that if your target measure has this form, and if you have some kind of ergodicity and L1 integrability assumption, some noise, then any measure, any p-preserving diffusion can be written in this form. And conversely, if you write a diffusion in this form, then it preserves this p. And here you have two things you can choose. One is Q, which is an antisymmetric matrix, and D is a positive semi-definite matrix. So basically, this gives you the general recipe of measure-preserving diffusion on Rn for distribution in this form. So this is very nice, and it had a lot of impact in machine learning because it means that then you can just start with that, and then trying to find some Q and some D, which are used for sampling. So for example, underdamped Langevin is the one we just saw before, where Q is essentially your symplectic matrix, and D only acts vertically, so in the fiber direction. Overdamped Langevin as Q is equal to 0, so it's completely reversible, and D is essentially arbitrary. It's usually constant, so this term disappears, and you just have D grad B plus noise. That's the overdamped Langevin. And Francisco also talked about some essentially metropetic system in which your V is essentially free energy, but essentially okay. So every measure-preserving diffusion can be written in this form. The problem with the recipe in that paper is that the proof essentially relies on some kind of Fourier transform to try to linearize your Fourier-Planck equation and to build this thing. And it's quite hard to do that on a manifold, just because Fourier transforms are quite hard to handle there. So it's kind of not clear how you can generalize this to manifolds. And so to try to intuitively generalize it, we're going to essentially, well, just replace dx with our smooth positive reference measure. We replace Q delta V, which is just some kind of map which takes your gradient, your derivative of the potential, and maps it to a vector field. So we're just going to take a general basic linear map from the cotangent space to the tangent space at each point. And we're going to replace our Eton noise with some Stratonovich noise, just because it's easier to handle on manifolds. But this is completely general. Okay, so if we start with a general diffusion on manifold, and so in this form you have a drip and you have noise, then your Fourier-Planck equation has this form. So now we're going to start by just saying what happens when we just have noise, and we want just to find a drift which makes the thing inside of this 0 whenever we apply f to e to the minus v, because that's going to guarantee that e to the minus v mu m is preserved. And when we do that, so when we just choose x to ensure that the thing inside is 0, then we get this x, essentially. So we have, this is the drift that you need to ensure that when you start with an arbitrary Stratonovich noise, then your process is still preserved. So this essentially gives you the d part of the previous equation. And then we have this part here, which is the q part, the antisymmetric part. And we have this xv plus y that we need to kind of understand what they mean on manifolds. So given this diffusion, then the Fokker-Planck equation, so applied to the target density, is equal to 0 if and only if y satisfies this thing. So essentially, given this ansatz, we get this equation which has to be satisfied for this thing to be measure preserving. And the thing is that this has to hold for, well, by analogy with the Euclidean recipe, which we want to preserve the measure whatever your potential is, we want this to hold for any p infinity. So in particular, we would like to hold as well when p infinity is a constant. And when p infinity is constant, this thing is 0. And essentially, this equation just implies that your y should preserve the reference measure. So if we use this fact and we just rewrite this into this form, then that's going to tell us two things. Essentially, that's going to give us the definition of y. First, for y to define a vector field using this equation, so y applied to p infinity gives you that, implied that this bracket here that we define is antisymmetric. So initially, we were not assuming that, but actually it's necessary for y as a differential operator to satisfy Leibniz identity. So we know that B must be antisymmetric, and I'm going to denote it y, A. And actually, if you're familiar with Poisson mechanics, this thing, given an antisymmetric, well, normally B is the Poisson tensor, but this is exactly the definition of the modular vector field of Koszul and Dufour. So basically, once you have a bracket and a reference measure, if you define the vector field such that on any function it gives you that, this thing is called a modular vector field in Poisson mechanics. And the point, okay, so if we just use this definition and just sub in for y, then we get essentially this measure preserving diffusion. And so this, so with some analogy with Poisson mechanics. So the point is that if you write this in Euclidean space, you recover exactly the diffusion of that they are derived in that paper. So this gives you a generalization of that formula, which actually works on any manifold. So that's quite nice. And essentially, you can see the interpretation of each term. So essentially, this part is the reversible noise component. This part of the noise preserves the reference measure. When you add this term, you preserve, well, your target measure. Then here you have basically your mechanics associated to the antisymmetric bracket. And here you have the generalization of the modular vector field. And together, these things preserve the target measure, but this one preserves only the target density, and this one preserves only the reference measure. So essentially, you have this nice formula. Okay, which works on any manifold. But one of the nice results about that paper was actually that the recipe was complete. So it wasn't just a diffusion, general diffusion that preserved your target measure. It was that any target measure which was preserved. So if you have measure preserving diffusion, it necessarily has this form. And so we want. Yeah. So smooth measure means at least C1. Yeah. So by smooth measure, I mean essentially what I'm going to say here. So essentially, now we want to understand whether we want to actually understand exactly what's going on. So we're going to try to understand the geometry that's going on behind the recipe. So let P, so before was just kind of an intuitive construction. But now let P be a smooth measure. And that means that locally, P can be written as f dx, where dx is the Lebesgue measure, and f is essentially at least C1 function. So basically, that's just the definition of P being one density. And once you have a one density, you can define basically a linear map, a morphism, between multi-vector field, so this is the set of K multi-vector field, and differential forms. which basically lowers the indices, and it's using the interior product. So basically, given a k multivector, this gives you a twisted differential form technically, but let's just say a differential form. Okay, so we have this map, and if P is positive, so globally supported, then this thing has an inverse, which we're going to call P sharp. And P sharp is, you can understand its statistical significance by saying when you apply P sharp to another smooth measure, it gives you the random negative, basically, of that measure with respect to P. So actually, this P sharp associated to this P flat is a vast, very large generalization of the random negative derivative when you restrict a smooth measure. So it's generalization restricted. Okay. Okay, but the important thing is that once we have these two maps, then we can follow Koszul and define the P rotationnel of a k-vector field, which is defined by essentially you take your exterior derivative and then you apply B flat and B sharp on site. And so this gives you a map from k multivector to k minus 1 multivector field. And it's entirely canonical because it only depends on your target measure and essentially basically the exterior derivative. And okay, so the key point, and basically this Koszul, and then, so Koszul introduced this thing but didn't give it a name, but then Dufour and Ariki called it the rotationnel, and they studied basically the connection with the modular vector field that we defined before to analyze quadratic Poisson structures. But the point is that here we don't want to do physics, but we just have a very natural operator which looks relevant to statistics given that B sharp generalizes the random negative derivative. Now the thing is that if you apply curl to curl, you get 0. So curl is a boundary operator. And moreover, on vector field, curl just restricts to the divergence, which represented by how much a vector field, the flow of a vector field distorts basically your target measure. So already from that, you can kind of see that this is going to be important in statistics. And the curl of curl is equal to 0 really is the generalization of divergence of curl is equal to 0, where this one is this one applied to the Lebesgue measure on bivector fields. And when you have a Riemannian measure and a Riemannian metric, you can identify k-vector field with differential forms, and curl P becomes essentially your co-differential. Okay. Now, a key result is that so on vector field curl restricted the divergence, and on bivectors, it becomes a modular vector field. So that thing that before we associated to a measure on an antisymmetric bracket, that modular vector field is exactly the curl with respect to target measure of a bivector. So now you can see also the relevance of curl with respect to the previous recipe, because essentially we can replace this by curl. Okay, so we have this general operator which enables to do basically some statistical calculus. Importantly, it only depends on P up to normalization. And now the key thing, so this is essentially what's going to give us the recipe of measure preserving diffusion on manifold. So basically when you have a measure, you can have measure on a measure space. And then you can simplify and you can go on measure on a topological space. A measure on a topological space are much, well, quite simpler than general measure on a measure space. The point is that when you have a smooth measure on a manifold, then that gives you a lot of structure. Because essentially that tells you that, well, basically this thing tells you that such measure defines some kind of homology, which actually you can show is isomorphic to the standard Durham cohomology. So basically that means that any geometric statement about the Durham cohomology tells you a statement about smooth measures. And in particular, curl P3, so multivector field for which the curl is 0, can be represented just as closed form. So any closed form is basically equal to an exact form plus a topological obstruction. And this is exactly the same with curl P3 multivector field. You can write it as a curl P, globally curl P of another multivector field plus a topological obstruction. Okay, so now we can derive the basic complete recipe on any manifold. We start again with diffusion. So in general drift and general noise. We write Fokker-Planck equation. So here L star is the Fokker-Planck operator applied to the smooth measure, which returns you a smooth measure. And the density of that smooth measure is this thing. so the divergence of a thing I call the focal Planck current. And the point is that L star of P is 0, so the focal Planck equation is satisfied, if and only if basically the divergence of something is 0, but the divergence is just the curl on vector field. And because we have the Durham cohomology isomorphism, that means that this thing, whose divergence must be 0, can be written as a globally curl of a bivector plus a topological obstruction associated to the isomorphism between the P homology and the Durham cohomology. So that means that any P-preserving diffusion has this form. So basically, you have the Shatanovich noise, which is corrected by some kind of dissipative drift associated to your noise. So this is just what you need to correct this. This is dissipative by itself, and together these things are basically the most general reversible diffusion associated to P. And then you have the antisymmetric parts, which is essentially associated to the fact that your focal Planck current is divergence-free. So you have for some bivector and some topological obstruction, the most general irreversible component, so antisymmetric part, is going to be this thing, which is L2P antisymmetric, this generator, which is basically a local focal Planck potential, which is basically the most general uncontractable manifold, plus the topological obstruction. So the nice thing is that not only we have generalized this to manifold, but it's completely canonical. So it's a complete recipe, it's completely canonical, only depends on your target measure, and actually removes all the assumptions that were needed in that paper, aside from smoothness. So when we compare this with this, we say that here we have 4 terms, and we have 5. But actually, on Euclidean space, this is 0. So actually, in general, we only have 3 terms, and here we have 5. And the presence of the other term is just because we split the curl of P in terms of the curl of the reference measure, plus essentially another part associated to the target density. So essentially, in general, we have 4 terms, and then when you decide to split P into a density and reference measure, then this decouples into 2 terms, this decouples into 2 terms. Essentially, this in Euclidean space decouples into that plus that, and this decouples into that plus that. So basically, okay, so this is the most general measure-preserving diffusion on any manifold. And as we've seen, this is basically just Durham cohomology, so it's a very, very old idea. But yeah, okay. So the completeness, essentially, we've seen is just based on the fact that because of the isomorphism between curl P and exterior derivative and its cohomology, the kernel of any divergence-free vector field, in particular the focal Planck vector field of a measure-preserving diffusion, is equal to the curl of a bivector field plus basically the P sharp of some kind of topological obstruction. The point is that, so forgetting now topological obstruction, this, you can think of this result exactly as a potential theory for measure. So just as in physics, we write the conservative force, one form, as the derivative of a potential function, and the electromagnetic two form as the gradient, as the derivative of one magnetic potential. Similarly, any P-preserving vector field can be written as the curl P of A. So this is really just your potential. So it's exactly the same idea as in physics, where you have some operator, in that case D, and in our case curl P, and we have some kind of conservation, and we write that, and because we have a conservation, we have a local potential. So essentially, yeah, this is again a very old idea, but just with a new operator, which is actually isomorphic to the old operator. But this is relevant to statistics, and this one is the one of physics. Okay, so there's actually some very deep connections between measure-preserving flows and Hamilton mechanics from a very general perspective. First, given any measure-preserving flow X, so just which is an equation of divergence P, when you locally write it in terms of P, well, basically a density times Lebesgue measure, then any such flow split like that, where this is just a sum of Hamiltonian vector field on the coordinate 2 planes. So basically, any measure-preserving vector field splits into Hamiltonian vector field on each 2 planes, plus some kind of term associated to the log density, or the score, because there's a derivative, which is actually very similar to a Poisson, the Hamiltonian vector field of a Poisson system. It's just that A doesn't satisfy necessarily the Jacobi identity. But yeah, so we have this very deep connection between P-preserving flow locally and Hamiltonian mechanics. And another connection is that if x and y preserve P, then the commutator can be written as the curl of x wedge y. And this is very similar to the statement in Hamiltonian mechanics that symplectic vector fields, which are locally Hamiltonian, the commutator can be written as a globally Hamiltonian vector field. And similar here, locally curl vector field can be written as the global curl of, well, basically something. So commutator of symplectic field is Hamiltonian, and commutator of measure preserving flows is globally curled. Okay, yeah. So basically we have this nice decomposition of curl PA, so the thing we use of our focal Planck potential, which holds for any reference measure. So curl P of A is equal to curl mu m of A plus interior product of the external derivative of the log density A. And this was proved by Kozul, I think, again. And actually, Kozul proved a lot of things about statistics. It's just he writes everything in terms of cohomology, so it's kind of hard to understand. But if you don't read French mathematics like me. But he proved like a ton of results of this form, which are really, really interesting. Because once you have this result, you can start to think, okay, so I know that for any bivector field, curl of P is measure preserving, and I know that at least locally, any measure preserving vector fields of that form. And I know I have this splitting, so I know I can kind of try to choose some A and some mu m such that this is 0, and essentially such that my measure preserving system is just a score-based dynamic. So a score is just a derivative of the log density. Because this is, well, basically this is kind of a linear, it's basically a small generalization of Hamiltonian mechanics. So it's quite simple. And the question is, okay, so how can I choose my potential and my measure such that this thing disappear? Another interesting thing is that before we've seen that curl mu m of A is exactly the modular vector field, so the generalization of the modular vector field, which, if you remember, was a map from function to divergence of the, well, of the vector field defined by A. So this thing, where log P infinity is F, so this is this, and the divergence with respect to reference measure. In particular, this is 0, if and only if this is 0, which means that all these vector fields, for any F, preserve the divergence, well, preserve the mu m. So essentially, so you get the statement that mu m is an invariant measure for the A mechanics, which is the set of this vector field, if and only if curl mu m of A is 0. And so that implies, because of our Durham cohomology result, that all the basically mechanics of this form, which have an invariant measure mu m, are the curl of a free vector field plus again some topological obstruction. So it's again the same idea, but now we've also characterized not only measure preserving dynamics, measure preserving diffusion, but also measure preserving mechanics. So basically, the set by measure preserving by A mechanics, I mean anything of this form, and by measure preserving, I mean that it has a basically invariant volume form. So an example of which is Hamiltonian mechanics, which is of this form, where A is the Poisson tensor, and mu m is a symplectic measure. But this gives you the general characterization on any manifold without any assumption. 38, okay. So now just some historical remark about the things I said. So first of all, the complete recipe in Euclidean space of 2015 was only using this result before the Lebesgue measure, because it was a focal Planck operator with respect to Lebesgue measure. So we only had to characterize measure preserving, basically vector field preserving the Lebesgue measure. And this was actually proved by Volterra in 1887. So a very long time ago, actually, Volterra proved that any flow preserving the Lebesgue measure is a divergence of an antisymmetric matrix, which is all you need for that recipe. So actually, in 1887, Volterra proved something which was far more general than what we had in this paper from 2015. So it's kind of a good reminder to read what people have done a long time ago, because well, these people from mathematical physics have done really a lot of stuff. The generalization of this result to manifold, I haven't seen it in the literature, but I think it was done by Durham, actually. Because I've seen a paper from Kodara hinting towards that, but I haven't exactly been able to pinpoint basically the whole history. But I think what I've written here was actually already known to Derham, basically in the 1930s. The curl operator in the form that I've written was defined by Kosul, who didn't give it a name. Then Dufour gave it a name when he applied it to quadratic Poisson structure. And Banstedt connected essentially, in the case of Poisson system, the modular vector field and the curl of the Poisson tensor. So essentially, these are basically all these ideas can be found expressed in kind of different ways, but by basically these people. And the nice thing is that because we have this isomorphism between basically the operator about associated to a measure and the external derivative and the cohomology of the external derivative, what this really means is that, result about geometry tells a lot about statistics. So here I'm going to talk about measure preserving flow in these talks, but actually this idea also really, really important in state discrepancy, because in state discrepancy, essentially you want to have measures that integrate to zero, but there are results about measures that integrate to zero are necessarily exact forms on compact manifold. And essentially that gives you can derive the Langevin-Stein operator directly out of very, very old results from geometry, just based on top result from the top Derham cohomology. And okay, so now a bit more into statistics. So basically, if we have some A for which this is zero, then as we've seen, that means that this basically we have I d log p infinity A is equal to curl p infinity mu m A, and this is true for any p infinity. So that tells you that essentially the score-based mechanics is just the curl of the token measure, and in particular is p preserving. And the nice thing is that that also gives you a general way to numerically implement these systems, because whenever your p infinity split into independent components, well, then the d log split into a sum, and all these things are linear. So here your vector field naturally split into the independent component, which gives you a natural way to basically approximate this by implementing all of this individually. And moreover, because all this vector field preserves the reference measure, because it's an invariant measure of all this vector field, then if you want to add a metropolis step, you're going to have no Jacobian of the invariant measure appearing. So essentially your accept reject step is just going to be an energy difference, just as in HMC. So this is actually the reason why we use Hamilton mechanics for sampling. Because in principle, you just want to have a vector field of preserved token measure. But actually, it's useful to have an entire mechanics which preserves some kind of invariant measure, because then that means that when you do a splitting, all of these are going to preserve your reference measure, and you're going to have no Jacobian of the reference measure terms. Okay. Okay. So actually, there's time, so we can build. Kind of build Hamilton Monte Carlo. So essentially, the choice now is now that we know basically we have all this recipe. The question is, how do we choose our A, and how do we choose our reference measure, and whether we want to use a mechanics or diffusion. But here I'm going to focus on measure preserving mechanics. The idea between Hamilton and Monte Carlo is just basically at least in this form, is that you're given a target measure P equal to e to the minus v mu m, where mu m is typically a Riemannian measure. And you're going to do the simplest thing you can do when you're a physicist, is that you're going to try to make a proposal by just viewing V as a potential energy. So you're going to use just mechanics. So when you're in Euclidean space, you can use the Newtonian equations. And when you're on a Riemannian manifold, you can just use the Riemannian metric associated with that to just find the curve, basically, version of this. And the reason why actually this makes sense from a statistics perspective, so here you have some kind of second order flow, so you need two initial conditions, so this is actually automatically a flow on the tangent bundle. And the reason why this makes sense from a statistical perspective is that the flow, this Riemannian Newton flow, preserves this canonical distribution on tangent bundle, where this is the Riemannian norm. And so here you have some kind of Hamiltonian, where you have your initial target density plus the Riemannian norm, and a Bézier reference measure is the symplectic measure, just expressed in Riemannian coordinates. And the point is that your flow preserves that, and the projection of that from Tm to M is precisely your target measure. So the point is that if you can sample from UH, and here you have a way to do that, because this is measure preserving, then samples from UH are going to project a sample from P. So essentially, this is the basic idea between Hamilton mechanics, is that, well, just very naturally, just using physics idea, you get something which actually makes sense for sampling. But actually, there's loads of advantage to using Hamilton mechanics for sampling. So first of all, okay, it's very natural. You just start with a potential. You automatically get basically mechanics preserving some kind of reference measure, so which are going to have no Jacobian. You remember that when we wanted to use Monte Carlo, so when we wanted to combine a deterministic proposal with a Monte Carlo step, we needed to find some kind of S map which makes the proposal reversible up to S. And that S needed to preserve the target measure. And in Hamilton mechanics, we have a natural choice of S, which is just the velocity flip, because this preserves your target measure, because it preserves both your Hamiltonian and the symplectic measure. So in particular, that result I wrote initially, now you can write it in this form. If you find an integrator on your tangent bundle or cotangent bundle, such that this is true and psi also preserves your symplectic measure, then you have, well, just as before, you can follow your integrator, then your accept-reject step is just going to be the energy difference, and if you reject, you're just going to flip the coordinates. You're going to flip, sorry, the velocity. And because you don't care about the velocity component of that thing, actually, that doesn't do much. So that's a pretty simple algorithm. And in particular, if you know the geodesics of μm, of the associated Riemannian measure, then you can very naturally just split the Hamilton vector field of H that we had before, that was just when we used Riemann-Newton equation. And you can split XH in this way and stimulate this, which can always be solved. This is very easy. It's basically a great vertical gradient flow. Then follow the geodesics, and then again follow the vertical gradient flow. So you very naturally you get basically this volume preserving mechanics and a way to integrate it when you do geodesics, which for example you do in Euclidean space, and so you get a very easy way to build this kind of proposal. And so a particular geodesic integrator, you, for example, on the sphere, you follow the geodesics, which is xt, then you xv just essentially changes your direction, then you follow the geodesic again, and this is exactly the same plot, but just with the shorter geodesics. So these are already some advantages of using Hamilton mechanics. It's a very convenient choice when you know the geodesics. There's another thing is that essentially these core-based mechanics, they always preserve your log density. So they always remain stuck on the density level sets. So whenever you use these kind of flows to samples, you're always going to have to at least combine it with something that changes the energy levels, the target density levels. And because HMC lifted the measure on M to a measure on TM, where the lift was a Gaussian, you can simply use basically the fact that, so essentially your Riemann-Newton flow was lifting P to a measure on a tangent bundle, which you can write into this form. In particular, if you sample from a Gaussian, this thing still preserves μh, so you can combine it with your algorithm that I wrote before, and you can use this to switch between energy levels. And so basically, you obtain that essentially HMC, very naturally, is just MDMC, the thing I wrote before, so Hamilton mechanics plus Monte Carlo step, combined with a heat bath, which is just a Gaussian sampling, which is very easy to simulate. And so the point is that if you know the geodesic flow, then essentially you can very easily implement a Hamilton Monte Carlo on a manifold, which is one of the reasons why it's very useful. But there's actually a reason why it's very powerful. It's not just that it doesn't have Jacobian term in the exact reject step. It's also that essentially you can find a class of integrators, mechanical integrators, which also preserve your energy very, very well. And essentially, you have a result from Hamilton mechanics, basically based on Hamilton-Jacobi theorem, which tells you that whenever you use an integrator which is symplectic, So it doesn't just preserve your reference measure, the symplectic measure, it actually preserves the symplectic structure. Then, any such integrator has a nearby shadow Hamiltonian whose flow is actually your numeric integrator. And in particular, this means that typically the energy doesn't change much because energy is conserved around during Hamiltonian mechanics, and that shadow Hamiltonian, which is basically the Hamiltonian function of this numeric integrator, is close to your target Hamiltonian, so your target basically energy. So basically, so in Hamiltonian mechanics, not only you don't have any Jacobian of reference measure, your energy difference actually remains quite stable, even if you travel quite far on your manifold. So that allows you, from a statistics perspective, to basically make proposals which are quite decorrelated from where you are. You can actually travel quite far and still get some good accept-reject steps. And so that's another advantage of Hamiltonian mechanics compared to other things you could use. And yeah, so aside from the symplectic integrator, you can generally use the Wolff theory of symplectic integrators, which tells you, well, one were the splitting methods that we discussed before, where you just split your Hamiltonian into different parts and you just simulate them one after the other. But another thing which is very useful is you also have basically a Lagrangian theory and generating function theory of symplectic integrator, which is very useful when you want to do sampling from manifold with holonomic constraints. Because on those, which happens a lot in statistical molecular dynamics, because in those manifolds you typically do not know the geodesic flow. So this kind of splitting integrators are not very useful. But on the other hand, you can build integrators using these basically mechanical integrators, and one of which is Rattle, which is used a lot for basically sampling for mesh on holonomic constraints. Okay, so we can ignore this last point. Okay, perfect, yeah. So basically just a quick discussion on how you implement HMC on manifolds. So two general classes of manifolds, one in which you know the geodesics and one in which you don't. So the one in which you know the geodesics are typically homogeneous manifolds. So you have some kind of Lie group acting on them. So in this case you have G, so you have your sample space is M, you have a Lie group G acting on M, it has an isotropy group, and you can write M as G mod K. So if you have a measure on that kind of manifold, then what you can do, so one thing you can do is to just say, well, my target potential energy, so my density on M, I'm going to lift it to G and view it as a basically function with symmetry on G. So a function on G which is K invariant. And so because you have an actual action of K on G, this gives you a momentum map. And in particular what that tells you, so the result from symplectic reduction, tells you that if I have some Hamiltonian action on my system over G, which has some K symmetries, then essentially J is going to be a conserved quantity. And the good thing is that if I set my conserved quantity to 0 initially, then the reduced space is exactly the tangent bundle. So it's actually my target space on the sample space, the one we wanted to implement Riemann and Newton. So basically I start from a measure on M, and instead of implementing Riemann and Newton system here, I lift everything to the Lie group because the Lie groups are very simple. And then I can implement everything there by just considering my Hamiltonian, my target potential, lifted as a basically potential with symmetries. No. You don't need compactness, but you typically need your manifold M to be a naturally reductive manifold, of which many are basically many of them have G which is compact, but not all of them. And for example, one which doesn't is the space of positive definite matrices, in which G is GLN. And in that case, M is basically, well, non-compact. Okay, oh, sorry, you say K? Yeah, so K is compact, yeah. I don't know if it's maximal. I know M. No, it's, no. I mean, I'm not sure exactly. So M, so in this, so basically actually, So maybe I was suggesting when I said homogeneous manifold, maybe we should restrict to M being natural reductive homogeneous manifold, because those are the ones which have an actual geodesic flow which is simple. So I don't know if that answers your question. Oh, no, not necessarily. No. For example, Stifel manifold is not symmetric, but it's naturally reductive. So it's more general. So basically in the class of this manifold, you have symmetric. Then you have, so you have, let's say, Riemannian symmetric. Then you have natural reductive homogeneous manifold, and then you have geodesic orbit manifold. So technically the thing I've said here, you can do for any geodesic orbit manifold, but the actual one you carry in statistics are all natural reductive. Essentially, it's, there's not that, there's Stifel manifold, Grassmannian manifold, space of positive definite matrices, their complex version, and when they exist, their hyperbolic version. And in all of these things, you can basically do the same trick of lifting your measure on M to a measure on G with symmetries. Your G, you want to set the construct quantity to 0, which just means that you want to start here, basically on G, and where P is the complementary subspace to basically the isotropy algebra. And here, essentially, then your Hmc algorithm is very simple. You just have this vertical gradient step, the momentum, and your geodesic is just the matrix exponential. So then you just do that, and then you project at the end, and you get Hmc on all these manifolds. So this is the first case. The second case is when your M is a level set. So this is the second very important case. And in that case, you can use essentially integrators from Lagrangian theory, of which the most important one is Rattle, which is a constraint version of leapfrog integrator. And one important thing, though, and this was shown by a paper recently by Lelièvre, Houches, and Stolz, is that actually you have to be careful because when you do HMC, you typically want to sample without bias. But actually, Rattle and your integrator need to be symmetric, reversible. But actually, Rattle is only reversible for small enough time step. And people actually, for a long time, were using Rattle, but were forgetting to check whether the time step was sufficiently small for the thing to be reversible. So you thought you were sampling without bias because you were doing HMC, but actually you were sampling with bias because you knew it was not reversible. So in this paper, Lelièvre discusses exactly how to basically add a reversibility check component to Rattle to ensure that the resulting integrator is the resulting scheme samples from your target measure without bias. And yeah, so basically, yes, actually, I can finish here. But the point basically about Hamilton Monte Carlo from here is that you can see that it's very natural. It has the shadow property of the integrator, which means the energy is well preserved. And also you have very, you have very natural way to implement them implement HMC on basically all the common manifolds, which are either of this form or of this form. But yeah, okay, yes, I'm done. So I'm going to leave time for questions.
You mentioned structure preserving integrators, mechanical integrators, and you mentioned preserving energy and simplicity, and also momentum up as well. And but I believe that you cannot preserve all three for a fixed step, or you have to choose two of them. Yeah. Okay.
Typically what you do is that you want to really go to preserve the specific structure rather than the energy. And the good news is that when you use discrete Lagrangian integrators, such as Rattle, then whenever you use discrete Lagrangian as a symmetry, then you preserve not only the specific structure, but also the symmetry automatically. So essentially, this the integrators that use the HMC are discrete Lagrangian integrator, which automatically preserve symmetry, but not energy. But then they have the shadow Hamiltonian, which cannot preserve the energy.
Okay, no more question. Okay, thank you.